Good day, Senior High! Welcome back to another episode of Learning General Mathematics here at STEAM GTV. I am Kiarra, your Kadu in today's lesson. This is a new day for fun and exciting learning. Together, let's be Math Husay, Math Talino, and Math Galing! As we begin today's lesson, I'm hoping that you have a pen, a paper, a book, and a calculator with you. Are you now ready? Lo and behold, it's time for us to discuss solving exponential equations with word problems. To begin with, let's start first by stating the objective of today's lesson.
So for the learning objectives, you're expected that at the end of the lesson, the students should be able to understand the definition of exponential equations, solve exponential equations, and apply exponential equations to real-world problems.
Now, let's start the discussion by having a real quick review. Let's see whether you can identify an equation, an inequality, and a function. This will help you understand our lesson for today's episode.
Now, let's have an activity for a quick review. I want you to put a check in the box if it's an exponential equation, and you have 15 seconds to do it. Time starts now. Now, let us try to see if you got correct answers. Actually, based on the listed expressions below, we only have two exponential equations. First is 7 raised to the power of x plus 1 is equals to 49, and 4 raised to the power of x is equals to 16. And the remaining expressions are, we have here exponential function and exponential inequalities. So first, among the given above, 7 raised to the power of x plus 1 is equals to 49, and 4 raised to the power of x is equals to 16 are exponential equations. They are equations involving exponential expressions and are consisted of only one variable.
Math Husay! Now that you already have the basic knowledge of what an exponential equation is, let's now start discussing solving exponential equations with word problems.
Let's start first by defining what is exponential equation. Exponential equation, it is an equation in which a variable occurs in an exponent. Example is 2 raised to x is equal to 81. 1/3 raised to negative x is equal to 9. These can be solved by using laws of exponents and one-to-one properties. So let us recall the laws of exponents, where we have 8 rules. And for the first rule, we have the multiplication rule, where a raised to m times a raised to n is equal to a raised to m plus n. Second, we have the power of a power rule, where a raised to m is raised to n, equal to a raised to m times n. Third, we have the power of a product rule, where a times b raised to n is equal to a raised to n times b raised to n. Fourth, we have the quotient rule, where a raised to m over a raised to n is equal to a raised to m minus n. Take note that a should not be equal to 0. Fifth, we have the power of a quotient rule, where a over b raised to n is equal to a raised to n over b raised to n, where the denominator should not be equal to 0. Next, we have the zero exponent rule, where a raised to 0 is always equal to 1. Seventh, we have the negative exponent rule, where a raised to negative x is equal to 1 over a raised to x. Always find the reciprocal so that the exponent will become positive. And for the eighth rule, we have the fractional exponent rule, where a raised to x over y is equal to y root of a raised to x. And lastly, we have the one-to-one property. If x sub 1 is not equal to x sub 2, then b raised to x sub 1 is not equal to b raised to x sub 2. And then if b raised to x sub 1 is equal to b raised to x sub 2, then x sub 1 is equal to x sub 2.
Since you already know the laws of exponent and the one-to-one property, let's try to apply what you have learned by solving the following equations. Let's try to solve the equation 3 raised to the power of x is equals to 9. For the first step, we have to rewrite each side of the equation as an exponential expression having the same base. So 3 raised to the power of x equals 9 becomes 3 raised to the power of x equals 3 squared. Now, we are going to use the law of exponent, which states that if b raised to the power of x is equals to b raised to the power of y, then x is equals to y. So if 3 raised to the power of x is equals to 3 squared, then x is equals to 2. Thus, x is equals to 2 is the solution of the equation to 3 raised to the power of x equals 9. For the last step, we are going to check the solution by substituting it to the equation. So we have the original equation, 3 raised to the power of x is equals to 9, where according to our answer, x is equals to 2. So let us substitute the value of x to the equation. So 3 raised to the power of x equals 9 becomes 3 squared equals 9. Now evaluating 3 squared is equals to 9. Thus, 9 is equals to 9. Therefore, our solution is correct. Let us have another example. Let's try to solve the equation 2 raised to the power of 3 plus x equals 32. Again, the first step is to rewrite each side of the equation as an exponential expression having the same base. So, 2 raised to the power of 3 plus x equals 32 becomes 2 raised to the power of 3 plus x equals 2 raised to the power of 5. Now, let us again use the law of exponents, which states that if b raised to the power of x equals b raised to the power of y, then x is equals to y. So if 2 raised to the power of 3 plus x is equals to 2 raised to the power of 5, then 3 plus x is equals to 5. Then we are going to transpose 3 to the right side. The equation then becomes x is equals to 5 minus 3, which leaves us with x equals to 2. Thus, x equals to 2 is a solution to our equation 2 raised to the power of 3 plus x equals 32. For the last step, check the solution by substituting it to the equation. So we have the original equation 2 raised to the power of 3 plus x equals 32, where according to our answer, x is equals to 2. So let us substitute the value of x to the equation. So 2 raised to the power of 3 plus x equals 32 becomes 2 raised to the power of 3 plus 2 equals 32. 3 plus 2 is equals to 5, thus giving us 2 raised to the power of 5 equals 32. Evaluating 2 raised to the power of 5 is 32, giving us 32 equals 32. Therefore, our solution is correct. Let us have a last example. Let us try to solve the equation 1/3 raised to the power of 3x is equals to 1/27. Again, the first step is to rewrite each side of the equation as an exponential expression having the same base. So 1/3 raised to the power of 3x equals 1/27. So according to our law of exponent, we can convert the fraction to a negative exponent. So 1/3 raised to the power of 3x equals 1/27 becomes 3 raised to the power of negative 1 raised to the power of 3x equals 27 raised to the power of negative 1. Since the exponential expression should have the same base, 3 raised to negative 1 raised to 3x equals 27 raised to negative 1 becomes 3 raised to the power of negative 3x equals 3 raised to the power of negative 3. Now, let us again use the law of exponents, which states that if b raised to the power of x is equals to b raised to the power of y, then x is equals to y. 3 raised to negative 3x is equals to 3 raised to negative 3. Now that they have the same base, let us now evaluate the exponent, giving us negative 3x equals negative 3. Divide both sides by negative 3, leaving us with x equals 1. Thus, x equals 1 is the solution to the equation 1/3 raised to the power of 3x equals 127. Now, for the last step, let us check the solution by substituting it to the equation. So we have the original equation 1/3 raised to the power of 3x equals 127. According to our answer, x is equal to 1. So let us substitute the value of x to the equation. So 1/3 raised to the power of 3x equals 127 becomes 1/3 raised to the power of 3 times 1 equals 127. 3 times 1 is equals to 3, so 1/3 cubed equals 127, where 1/3 cubed is 127, giving us 127 equals 137. Therefore, our solution is correct.
Now that you already have an idea on how to solve exponential equations, let us try to apply what you have learned in real-life situations.
So now that you know how to solve exponential equations, let us now apply it in real-life situations through solving word problems. Let's try word problem number 1, which is about the law of exponential growth. The population of Region 7 in the year 2000 can be approximated by the formula P equals AO times E raised to the power of 0.125 times T, where T is the number of years after 2000 and P is expressed in millions. Supposing the formula is true until today, and in 2023 the population of Region 7 is approximately 30 million, then what was the population in the year 2000? Let's try solving this. Step 1. The first thing we must do is to write down our given statements. As stated in the word problem, T is the number of years after 2000. Since we are looking for the population in the year 2000 and our given is 2023, we can say that T equals 2023 minus 2000 equals 23. 23 is then our final value for T. Looking at the word problem again, in the year 2023, the population of Region 7 is approximately 30 million. And since P is to be expressed in millions, we can say that P sub 2023 is equal to 30 million. The next step is to solve for AO. Using the given formula, P equals AO times E raised to the power of 0.125 times T, we can say that 30 is equal to AO times E raised to the power of 0.125 times 23. 30 and 23 being the respective values of our given statements T and P. Since we're finding the AO, we divide both sides by E raised to the power of 0.125 times 23. After that, we can cancel out E raised to the powers of 0.125 times 23. Then we are left with AO equals 30 divided by E raised to the power of 0.125 times 23. And using our calculators to solve it, we are then left with the answer, which is that AO is approximately 1.69. Therefore, the population in Region 7 of the year 2000 is approximately 1.69 million. Let us now move on to the second word problem, which is about the law of exponential decay. The half-life of a radioactive substance is the time it takes for half of the substance to decay. The formula describing the amount of substance remaining after time t using the half-life is given by A times T equals AO times 1 over 2 raised to the power of T over H. Suppose that the half-life of a certain radioactive substance is 15 days,
and there are 100 grams initially, determine the amount of substance remaining after 30 days. Let's try solving this. Step 1. Once again, we are to write down our given statements. The formula to be used is A times T equals AO times 1 over 2 raised to the power of T over H, where A times T equals amount at time T, AO equals amount at time T equals 0, which is the initial amount, T equals time, and H equals half-life. The values of these statements are as follows. T equals 30, H equals 15, and AO equals 100. The second step is to evaluate A times T equals AO times 1 over 2 raised to the power of T over H. Through substitution, we can then have A times 30 equals 100 times 1 over 2 raised to the power of 30 over 15. 30 over 15 can be simplified to 2. That is why we have 100 times 1 over 2 raised to the power of 2. 1 over 2 raised to the power of 2 is equal to 1 over 4. 100 times 1 over 4 is then equal to 25. Therefore, the amount of substance remaining after 30 days is 25 grams.
Mahtalino! Let us now summarize what you have learned for today.
So we have here the summary of key ideas of today's lesson. So again, exponential equation is an equation in which a variable occurs in an exponent. Next is the one-to-one property of exponential functions, and it is useful in solving exponential equations, which states that if b raised to the power of x sub 1 is equal to b raised to the power of x sub 2, then x sub 1 is equal to x sub 2. Next, we have here the formula for describing exponential growth of a population that is given by a times t is equal to a sub 0 times e raised to the power of kt, where at is the population at time t and a sub 0 is the population at time t, which is equal to 0, and t is the time and k means the constant. We also have the formula for describing exponential decay of a population that is given by b times t is equal to b sub 0 times e raised to the power of kt, where bt is the population at time t and b sub 0 is the population at time t that is equals to 0, which is the initial population, and t is the time and k is constant. Lastly, to solve problems involving exponential functions, let us follow these steps. First, identify the given information or quantities. Next is to determine the equation that describes the situation, then substitute the given quantities in the equation, and then solve the unknown quantity.
Great job, Senior High! Magaling! You have successfully finished our virtual lecture, and I am beyond glad to know that you have nailed it. That's it for today, but learning doesn't end here, so I hope you study in advance with your book. Again, this is Kiarra Carreon, your kadu in solving exponential equations with word problems. I hope I help you become math husay, math talino, and math galing!